Hello class, this is CSE-5250, sections 2 and 60, week 5, spring 2026. I'm Giovanni Orijuela, and let's talk about your benchmarking project. I guess the first question is, what are we benchmarking? And you actually have the program already. Assuming you had followed along with the last two programming assignments, we wrote a pi estimating program. That's what we're benchmarking. Right. So, the pi estimating program that you had written should be the one that uses a mutex for enforcing mutual exclusion and has the bug fix that lets it run with an arbitrary number of threads and an arbitrary number of terms without the risk of having any terms being lost. Okay, with that in mind, let's look at the instructions for this project. As a preliminary step, take note of how many CPU cores are available on your system. You're going to want to open up your system's equivalent of System Monitor or Task Manager. In the case of Ubuntu, that is, well, System Monitor. Here it is. It says I have 6 CPU cores available to me. So, we are not benchmarking against each other or against computer versus computer. Rather, we are eliminating the variable of number of CPU cores available and just locking ourselves in to just using one specific machine. Rather, we are benchmarking against different workloads and different numbers of threads. So this would not make sense if you ran this on one computer and then did it again on a different computer. No. We want to eliminate as many variables as possible, lock into just one machine. We're going to run this program on one machine. Alright, I'm going to open this program up in the terminal. It was pi mutex 3 in my case. This was the one that had both the mutex lock and the bug fix. And to remind ourselves as to what we are to type in, when you run this, you have to include the number of threads followed by the number of terms. So let's just keep that in mind as we run this program. /pi mutex 3.c. No, not .c. The executable has no file extension. If I press enter and have nothing else, it does a segmentation fault. Now, let's do it the right way. One thread, 1 million terms. And it's gonna give us an estimated value for pi. Okay, but how do we get the right time? How do we get the time for that? Well, there's a time command that we can add before this. You're gonna want a real time for this. So get the real time. It ran for 5 milliseconds, and you will be running this combination of thread count and work size in the table here. So this is a table that contains example data, just, well, as an example. Ideally, you want to run each combination of work size and thread count as many times as you can get away with. Even if you have to run your computer overnight, if you can find a way to automate that, that's even better. But I say at least 5, but I would go for as high as 30. In general, the more trials, the better, because then you can just take an average. Okay, so this run was for one thread and 1 million terms. Again, it would be advisable to do each combination of thread count and term count as many times as possible, at least 5. I would recommend at least 30. You would then take the average of all of those runs and just punch it into the table. So eventually in here, we would take all of these real-time runs and average those out and get something like 4.4 milliseconds. That is already fast as it is. And you'd be thinking to yourself, if it's already that fast, did parallelizing it do any good for it? We'll get to that in a little bit. So, for each term count, you're gonna keep doubling the number of threads. So, let's do 2 threads now. There we go. Let's start it again. Okay, now it's running with 2 threads in 3 milliseconds. That is barely faster than before. I'm going to double the number of threads again and try it with 4 threads. It's running in 2 milliseconds now. If I do this again with 8 threads, that's going to reach the limit of how many threads I can run at a time, given this is a 6-core system right now. Whatever times you get, punch them in as an average into your table. So in this case, I would have gotten, say, times such as 4.4, 4.4, 3.8, 3.4, and if I continued this with 16 threads, it might reach a point where I get a slowdown. That's because there aren't enough CPU cores to go around, and the system simply just can't run that many threads at a time. So in this case, it might be some combination of settings changed or software updates that I am getting different times. So in here, I am getting 3 milliseconds for 16 threads, 3 or 2 milliseconds for 8 threads, 2 milliseconds for 4 threads, 3 milliseconds for 8 threads, 3 milliseconds for 2 threads, and 4 or 5 milliseconds for just 1 thread. So let's keep a mental note of that. I'm just gonna punch those into the table really quick. Let's call that 5. You're gonna want to be more precise than I am. You're gonna want to keep note of all these times and then take an average of them all, as I mentioned. So let's just call that 3 for the sake of example. For 8 threads, let's call that 2. And for 16 threads, let's also call that 2. So what you should find, assuming this program was programmed correctly, is the more threads you have, the faster it's going to run. And if you look closely, that is what we get here. So with 1 thread, it's going to run 5 milliseconds. For 2 threads, it's going to run 3 milliseconds. So 5 divided by 3, that's a 1.667 times speed up. So we can just punch that in the second table here. So you're going to make 2 tables. The first one is the times, and the second one is the speed ups. So we also get a similar speed up for 4 threads, and then for 8 threads, that is a speed up of 2.5 times. And with this setup, it feels like it's petering out at 8 threads, which makes sense because, again, this virtual machine is only 6 CPU cores that can only ever run 6 threads at a time. If you have a more powerful computer available to you, what I would recommend is to just push that computer to its limit, expand this table as far as you can. If you have a 16-core 32-thread machine, for example, add a column for 32 threads. However you're able to do these benchmarks, you are going to repeat this process of term count and then increasing thread counts for each of these term counts. So let's do it again with, let's just get to the chase. Let's do it with 1 billion terms and start it with 1 thread. So 1 billion is, under the short scale, that is a 1 followed by 9 zeros. Okay, now it's taking a significantly long time to run. That is what? Nearly 3 seconds. Let's call that 2,770 milliseconds. I'll just punch that into the table here. If we did this for 2 threads, would we get a speed up? Yes, we do. Look at that. We have ran this thing in roughly half the time. And if we run this a couple more times, we should find that the runtime is going to average around 1.4 seconds. Let's call that 1,450 milliseconds. There we go. Punch that in. Let's try this again with 4 threads. Okay, so it looks like it got cut in half again. Let's run this a few more times. Again, be more accurate than what I am showing here. Run this for as many times as you can and then get an average. At least 5, but I recommend at least 30. Let's call that 750 milliseconds. Okay, now let's try it with 8 threads. Seems to be bottoming out at, okay, so we would expect that for something like this, we expect the runtime to be cut in half again. But it appears that I'm reaching the limit of this system here. So the speed up is not quite a 2 times speed up again anymore. So we'll just take note of that and just write, and I'm just gonna write in 580 milliseconds in the table here. Okay? Okay. Final one, that is 16 threads. Let's call that 520 milliseconds. So now we can repeat the process of filling out the second table with the speedups. So in general, for each row, you are dividing each of the times in each cell by the... No. Let's go back. It's going to be, for each cell, the time of the 1 thread case divided by the corresponding time for the increased thread count. So In the case of 1 billion terms and one thread, that's just going to be a one-time speed up because that is what we're comparing to. If we're going to compare the two-thread case against the one-thread case, that should be 2,770 divided by 1,450. So I have a calculator off screen, and it's saying I have a 1.9 times speed up. Similarly, it's going to be the same thing for the 4-thread case, except that is 2,770 divided by 750. Calculator is saying it's a 3.7 times speed up. 8-thread case is 2,770 divided by 580. That is a 4.8 times speed up. And the 16-thread case is going to be 2,770 divided by 520. Calculator says a 5.3 times speed up. So that is what you're going to be filling out in these two tables here. It's for the first table, how long did this program run? In the second table, how much faster did this program run with more threads compared to the one-thread case? And now, for part 3, you have a set of 4 questions you are to answer. Where do you think the sweet spot is for thread count? Was there a thread count that consistently had the best result? It's hard to define what best is, because what is considered best is going to have to depend on the context. But what do you think was the best thread count? If you had to log into just one specific thread count, what would you pick? Number 2, where do you think the sweet spot is for workload size? So now this is a little different. You notice that for the smallest work size, that was 1 million terms, we had times that ranged from 5 milliseconds to 2 milliseconds. But for the 1 billion case, that ranged from 2,700 milliseconds to 500 milliseconds. So what this question is asking you is this: at what point does it become more beneficial to run the program with multiple threads? Number 3, do you think this was a worthwhile speedup by the number of seconds saved? How about proportionally? So compare the columns one by one. How do you think the time savings is worth it? Like 5 milliseconds versus 2 milliseconds for the 1 million term case versus 2,770 milliseconds versus 520 milliseconds. Is the speed up worthwhile? But how about proportionally? In the 1 billion case, it's going to be, well, that's what you're going to compare to. That's your benchline right there. Your baseline, I should say. But with 16 threads, you got it to run 5 times faster. Is it a worthwhile speedup? And number 4, this is where Amdahl's law starts to show up here in a way. I guess theoretically, if we wanted to be thorough, we would be doing this on an infinity core machine. So we would always have resources. We would always have CPU cores on which we can run threads. But don't worry about it right now. The question is, at what point did he stop seeing a speed up? So we got this program to run. But at some point we're going to hit a limit. Well, Amdahl's law says we're going to hit a limit, and that limit is basically a theoretical limit based on how much of the program can be parallelized in the first place. But long before we hit that, we're going to hit a limit with our own hardware. We're going to hit a limit with the operating system. We're going to hit a limit with the code itself. Because you can't just cut an instruction in half. We're going to hit some limit and we're just not going to get any more speed up. Either way, we are going to hit some limit. So at what point did you start seeing a speed up? Or I guess, in a situation like, in a case like this, we still got speed ups and speed ups and speed ups, but at what point did the speed ups become less worthwhile? At what point do you feel like it's starting to go into diminishing returns? Those are the 4 questions you are to answer. What was the sweet spot for thread count? What was the sweet spot for workload size? Do you think the speed ups are worthwhile by amount of time saved, or just the raw speed up by itself? And at what point did you stop seeing any speed improvements? Did you get worsening results? Did you get results that were slower than the last? So these are the questions you're to answer based on the tables that you fill out. So that is your whole project. This project is due, I have it set to be due on the 28th of February, and the assignment officially closes on March 2nd. So the late policy that I have is the main assignments have a 1-week grace period. I have a shorter grace period for these mission critical assignments. It's a 2-day grace period. So make sure you have it submitted within 2 days of the original due date for the benchmarking project. I gave you such a large amount of time because I don't know if you noticed, but there's a winter storm warning right now. So just in case your power got knocked out because of the storm, basically I'm giving you a little bit of a time buffer just to make sure that you got it working in time despite any potential weather issues. Okay? Did I say 28th? I meant 27th. I have my calendar set to Monday is first, so I always get Friday and Saturday screwed up. So I might have set it to be either the 27th or the 28th. It should be the 27th, but I'll have to double check. But either way, you should have a 2-day grace period between when the assignment is due and when the assignment closes. Okay? Alright. So that's going to be the instructions for your Pthreads project. If you have any questions, let me know. And next week, I'm going to gently ease you into the next chapter of the text, and that is OpenMP. In my opinion, it's going to be a lot more fun to work with OpenMP simply because we have, all the work we had to do to make thread handles and all that. A lot of that is abstracted away when we get to OpenMP. Also, you can work on a Windows machine for OpenMP. So, in my opinion, it's going to be a lot more exciting to work with OpenMP compared to Pthreads. Alright, that's going to be it. See you next week. And if you have any questions, let me know.